Okay, well, welcome grade 9s, welcome back. Welcome back. I know you miss me so much, and there's no point in denying it, because I know. And the more you protest and say that you didn't miss me, the more I know how true it is. So you know what, there's nothing you can say, don't worry, I know. And listen, we're ready to have some more fun together, right? Learning some science and some technology and stuff, everyone's favorite topic. And yeah, so this semester, you have something else with me. It's not a science class this time, okay? And I'm just going to talk to you, before we talk about the first lesson, we're going to talk a little bit about the course. Okay, now I think in your course outline it says medical technologies. Yeah, well, let me just tell you a little bit about where that comes from. Years ago, when we started the program, it used to be called the pre-AP program, because we were considering having AP, which is advanced placement classes. But then we decided that it was better just to make it more of an enriched program, and that's where you come in with the STEAM program, right? Science, technology, engineering, arts, and math. So what I'm going to be doing with you here is more on the technology side, okay? So this is partly a science course, partly a technology course. Partly we're going to do some enrichment for you so that you have a head start into grade 10 and 11 and 12, okay? And that's part of the course. And so like we want to feel like once you get into grade 11, especially when you're joining the other students in the normal university level courses, that you feel like you have a strong start and that you are well prepared, okay? So that's part of it. So we'll be doing some science, but also we'll be doing some tech. And so let me explain how it goes. And even though it's called medical technologies, I really call it just generally speaking, a technology class, because really the sky is the limit. We can talk about any kind of technology we like in this course, okay? It's kind of wide open. So one of the first things we're going to be doing is talking about ultrasounds and CAT scans and X-rays and MRIs and, you know, dog scans and PET scans, right? Well, I mean, it's only fair if there's a CAT scan that we should have a dog scan, right? And there's, not even going to lie, there's something called a PET scan. And a PET scan does not mean you can scan any pet you like your dog or your cat or your bird or your fish or whatever you kind of pet you have. But we're talking about something called positron emission tomography. Now, do you really know what a positron is? Would you believe it's like antimatter? Because it is. And you know, it's closely related to something called uncle matter. Okay, no joke. Seriously, anti and uncle matter. All right, see, you miss me, right? I know you did. I can just picture you listening to that and just, wow, it just makes me feel good. Okay, so listen, here's how the course goes, okay? So I'm going to be doing a few modifications. We have to, because you know that we have this annoying pandemic we're still in the middle of, and that's not going to change anytime soon. So we're going to do a little switch here, module 1 and module 2. We're going to start with sound, X-rays, CAT scans, and MRIs. We're going to start with that, and then number 2, we're going to do medicine in space. So we're going to talk about, at first at least, medical technologies. And you know, I cannot really explain well to you what an ultrasound is unless you know how sound works, like what sound physically is and how we use it to create the images that you see in an ultrasound. Okay, so we're going to do a grade 11 physics on sound, a physics unit on sound. Okay, and if that scares you, it shouldn't, because all the math is grade 9 level. In fact, we did harder stuff already. Okay, so don't worry about that this unit is great for grade 9 and it's fun. Okay, at least I think it's fun because you're gonna like it. Okay, you're gonna like it. I think so anyway. Okay, we'll see, but I have a hunch that you'll like this unit. And yeah, that's gonna be some of the science that we're doing. Okay, and then we'll do medicine in space, where you are actually going to do a research project on, you know, when you travel in space, there are many potential medical risks. One of them is the risk of exposure to radiation, because without the protection of Earth's magnetic field, you are exposed to ionizing radiation in space, and your spacesuit, newsflash, does not protect you. Neither does your spaceship, for that matter. Okay, and yeah, you know what? A legitimate question is, how do we deal with these kind of medical issues in space? Plus, without your friend gravity around, okay, if you're going to take a trip to Mars, when you get to Mars, you won't even be able to walk once you get there. And the reason why is because you haven't used your legs for 6 months. And muscles are a funny thing. You need to actually use them, guys. Okay. And the funny thing is when you're living here on Earth, you use them all the time because you're always fighting gravity. Okay. But if you go to outer space, okay, one of the problems, it's a major problem too, it causes all kinds of medical problems, is lack of use of your muscles. See, even when you're just sitting there listening to this, gravity is exerting pressure on your spine and other bones and stuff like that. And pressure actually strengthens your bones. So when you chew on food and stuff, that actually strengthens your jawbone. If you lose a tooth, you're missing teeth. Okay, like some people have their teeth rotten and getting pulled out or whatever. If you don't have something in there, your jawbone will deteriorate. And maybe you've seen like very elderly people with deteriorating jaws. It makes them look incredibly old. Okay, yeah, it doesn't have to be that way, because if you keep a healthy mouth, okay, and keep pressure on those bones in there, they can stay healthy your entire life. And so when you go in space, here's your problem. You're not going to put all that pressure that strengthens the musculoskeletal system of your body, so your muscles and bones, is gone. Okay? And when it's gone, you're just floating around. You're not using muscles. It'd be the same as if you were to lie in bed for a month. Okay, so if you stay in space for a month, you could see what that feels like just by lying in bed for a month and never getting up. And then when you try to get up after a few weeks, you'll find that your legs aren't working so well anymore. Okay, and your muscles have atrophied and you've lost a significant amount of muscle mass. So these are kinds of problems that exist when you're traveling in space. Okay, so you're gonna be doing research projects on that and presenting them to the class. And so we'll talk about how we do that after we do the sound unit. Okay, so we'll get warmed up with the sound unit and then we'll do that medicine and space thing. And then after that, we're going to be not doing this one. It's unfortunate. Normally, first aid and remote medicine, what we used to do was every year we would do a 3-day field trip to a camp that's outside of Ottawa. And we do all kinds of leadership activities there. And one of the things we would do is we would train you on how to deal with a remote rescue. Let's say you're camping, someone is injured. How do you deal with the situation when maybe an ambulance is not so far, not so close, okay, like that? It's not going to arrive in under 5 minutes, kind of thing. But you could be waiting for hours for assistance, and what do you do, okay, in the meantime? And so we would do that normally, and we'd actually do the rescue, and it's a really fun trip. We can't do that this year. I think that's obvious. Okay, so that's canceled, unfortunately. One of the many unfortunate things that got canceled this year. All right, so anyway, after that, some software. So I think this is very useful in today's world. Okay, my son's in software engineering. You know, like you can write yourself a ticket to a job, okay, for a career if you know a little bit about programming. Okay, and I think it's a useful thing. I think it should be something as part of every child's school, is learning how to program, even if you never use it. Just like math is important, even if you don't become a mathematician, right? And so just some basic understanding of how software works and how programming works. And so we might do something like that. My son's grade 9 Enriched class did Scratch programming. We'll look at that. I'm going to talk to Mr. Brash. I used to teach computer programming at our school back when the dinosaurs roamed the earth, you know. But I still could do it, but like now, you know, Mr. Brash teaches software in the senior grade, so I'll ask him what he thinks we should cover just for a couple of weeks in this course. Okay, normally we do some labs, but that's another one that's going to be a little hard. I'm going to put a question mark there. I think we might do it together as a class. some experiments, but unfortunately you touching the equipment with, you know, we don't want to spread the virus, right? So we try to keep people gathering and touching equipment like to a minimum. And so you know all that from already from our science class, unfortunately. Okay. All right, now one more thing is normally we do a construction project of some kind. Now to give you some examples of construction projects we've done already, virtual reality, we built a computer. Okay, we got the headset, we got that going, and we did a research project on that over the last few years. Okay, we've been doing new software and new tools. We have like chemistry tools in there and like other educational software, plus some fun games. Okay, so that's one of the things we did. Another thing was we did a hover chair. Okay, so that was really fun. Another thing we did was lie detectors. We did Lissajous figure generators. I'll be showing you all these projects. We did a tornado generator. And before you get excited, Jacob, it's not one that will destroy the city. Okay, but maybe one that will destroy like an ant farm, you know, or something like that. Just a small scale one, but it was fun. Vortex cannons, that was a good one. Yeah, I mean, there's a whole host of projects. Some people built their own little robot from a kit and did some software with that. And so these are all projects that we do, but normally we would do that over the course of 5 months. Now we only have 2 or 2.5. That's not a lot of time. So we'll see what we can do. I'm hoping we'll do something like that, but it's going to be a little hard this year the way things are at school. So I can't make any promises. So I'm just going to put a question mark here. But don't worry, I've got lots of ideas if we need to do... Oh wow, my pen is acting weird. I got to make sure that that is working. Oh no. All right. There, that's better. Okay, so we'll see what we can do, but don't worry, I've got lots of things I can plug in. You know, like I've been teaching a long time, so there's lots of things that we can replace and take one thing out, put something else in, and that's it. Okay. Now here's the thing: how you get evaluated. Sometimes you're just going to get a traditional quizzes and tests. Okay. So sometimes we're going to have that, like in the sound unit, we're going to have quizzes, we're going to have tests. Okay. We're also going to have homework assignments, and I expect to see homework really strictly enforced this year. Okay, this course, science, I wasn't too strict about it, but in this class, I've decided to, this is going to be an important part of the mark, is you have to submit any homework you do in OneNote, and that is crucial. Okay, so forget the log book, that's not going to happen, but in OneNote, oh no, my pen is not working at all. Okay, let me see if I can fix this. So in OneNote, guys, I'll just talk while I'm trying to fix this pen. In OneNote, the deal is you're going to have to submit all your homework, okay? So that is crucial. Sorry, I'm just replacing the tip of my pen. Okay. So here, I'm going to cross this out, and I'm going to write OneNote. Oh, it's still doing it. Oh, I don't know why it's doing this. All right, I'm sorry. I'm going to have to do the best I can with this. It's writing OneNote. Well, this is going to be really fun today, me teaching. My pen not working very well, but I'll do the best I can. Okay, sorry, I apologize for that. All right, hopefully that'll work. All right, the joys of technology, okay, and teaching online lessons. Okay, so you're going to have to submit homework, okay? You're going to have to submit homework. Oh, wow. This is my wonderful cursive, I guess, here today. Homework. There you go. Okay, well, I'll do the best I can writing with this thing, but yeah, for some reason when I take the pen off the screen, it is not releasing the stylus, which is odd. Okay, well, maybe it's working better. All right. Okay, so anyway, I'm not going to waste any more time with this part here. We talked about like the construction project, so some information there, and you can forget about the due dates. That has all changed. So I just wanted to show you the old outline. I'm going to have to change it significantly this year, but to give you some sense of what we're going to do. All right, now without further delay, let's get started. So the first thing we're going to be doing is we're going to be talking about sound. Okay, now I have an outline for you here. Okay, and I want to show you this outline. And just like we did before, we're going to do 2 lessons a day in this outline. So the first 2 lessons, so this is today, okay? So this is like your day 1. Wow, that's going to drive me insane. Day 1, okay, lessons are going to be like that. Just the first 2 lessons there. And so we're going to talk about these things in a moment. And so like before we can really talk about sound, we have to understand waves, how waves work themselves. Okay, because waves is a, you know, understanding the properties of waves and everything is how we're going to understand how sound works in the first place. Sorry, I'm just really trying to make this pen work. And it really doesn't seem to want to work for me for some reason that I don't understand. Anyway, well, I'm going to make do. And I'm sorry I keep fiddling with that. It's just going to have to do some writing, and it's not going to be easy. So you'll forgive my messy writing, messier than usual, that is. All right, let's get started, okay? So the sound unit. Now there is some homework. Now, by the way, this homework you will find in a copy of the online textbook that I already gave you a link to. Okay, and I shared it with you so you could read it. Okay, so it's a grade 11 textbook, but like I said, don't be afraid of that. You'll be able to do the homework easy, super easy, no problem. Okay, in fact, we've already covered some of the basic units and everything that that you're going to need in science in grade 9 already. Okay, so we're going to be looking at some of these things, and we're going to be yeah. Okay, so let's just get started. And the first thing I want to show you is some animations actually, okay? So I prepared these ahead of time. Okay, so here's the deal. There are many different types of waves. Okay, so I'm going to show you these one at a time, and I'm going to label them for you in my terrible writing the way it's going to be. Okay, so this wave is called the transverse wave. Now you can see it here, your transverse wave. And the transverse wave, the thing about it is if you watch one of these red particles, the red particles go up and down. So here's, if you just watch one of the red guys, they're only moving up and down. In fact, all the dots only move up and down. It's a little bit like, it looks like they're moving up a hill or something, but no. They're actually just going straight up and straight down and straight up and straight down, every single dot, okay? Now, waves like this are a familiar shape to us because water waves are like this, okay? And here we have what are called crests and troughs, okay? The crests are the peaks of the waves, and the troughs are the valleys, okay? So we have peaks and valleys, or crests and troughs, okay? And the distance between 2 crests is called a wavelength. The distance between 2 troughs would be the same distance, so that's also a wavelength. In fact, the distance between one point on the wave and the same point on the wave, next wave over, is always a wavelength, okay? And it's actually physically a length, like, you know, you'd measure it in meters. These waves have a wavelength of 3 meters or something. That would be their wavelength. All right, so those crests and troughs, okay, peaks and valleys, waves like that, water waves in other words, are called transverse waves. Okay, now here in my second example, I have something completely different. So in this case, we have what's called a longitudinal wave. Okay, Now, a longitudinal wave is actually the yellow thing at the top. So I'm going to ignore the blue wave at the bottom. That's a transverse wave at the bottom, same as before. So here what you're seeing is waves in like a spring or something, okay? So imagine like a spring, like a slinky. And what you're doing is you're squeezing this slinky on one end, stretching it out, and then letting it go, and then you'll see this wave action propagate down the length of the slinky. We call these longitudinal waves, okay? Longitudinal means parallel, and so what's happening is these, if you watch any one of the lines move forward and back as the wave moves from the left to the right-hand side of the screen, okay? So these are longitudinal waves. See, there's no up and down movement this time, okay? No up and down movement, only back and forth. Now, if you contrast that with a transverse wave, so here we see the other type of wave, see how different it is. Now, they're both waves, okay? But with transverse waves, we get peaks and valleys, or crests and troughs. But with longitudinal waves, we get compressions, they're called. So that's here, this area here where the spring is compressed. And then in between the compressions here where it's spread out, they're called rarefactions. That's the opposite of a compression. Okay, so that is a second type of wave. Now there are other types of waves, okay, that are variations on these two. So watch. This next one is called a torsional wave. Okay, so that's a twisting wave is another way of saying it. It kind of looks like a transverse. You kind of see peaks and valleys. But what's happening is there's a twisting action in the medium, and that's why we call it torsional. That means twisting. Okay. Now here in this picture, here I have transverse and longitudinal waves. I see a spring can carry both of those kinds of waves. Okay. So that's just another way of looking at transverse and longitudinal. What do I have here? I think I have a two-dimensional longitudinal wave here. Yeah, okay. So if you look at the red dots here in the picture, there's one there and there's another one there. Oh, I centered it. Okay, there's another one there. Notice how these red dots move forward and back, not up and down, but forward and back, okay, as the waves go by. And there's a source here at the center that's emitting those waves. Okay, oops, I keep tapping on something. Anyway, there's a source here at the center that is creating waves. Say you're dipping your finger up and down in the water, okay, or in the medium, and what's happening is you're creating this disturbance that travels out in circular waveform away from the source. We call these ripples sometimes, if it happens to be water waves. But if they were sound waves, this effect would be happening in the air itself. You wouldn't see them, of course, but you would hear them. Okay, now, one more thing. I think here I have another visualization of a longitudinal wave. So here you watch the red dots just move forward and back. Okay, so in other words, they move in left and right, vibrating back and forth. All the dots are doing that. We're just highlighting two of them for you. And here you can see the terms compression and rarefaction. Now, these kind of waves have wavelengths too. That's the distance between two compressions would be a wavelength, right? All right, so those are all the types of waves. Now, I'm going to label a diagram like this for you, okay, on the next slide, like in a moment, okay? Like in 2 slides away, I'm going to label this. But for now, let's go through and talk about something called frequency and period, okay? Now, here's the deal. Here we notice, I'm going to go back to my little picture of the types of waves. What you notice, no, actually I want to go to the top one. What you notice here in this first one, okay, is look at the red source. So imagine you're holding, okay, this red block, and attached to it is a string. And what you're doing is you're moving your hand up and down, and that your hand moving up and down is creating the crests and troughs that travel away from the source as a wave, okay? Now, here's the thing. Frequency is how many times you go up and down in 1 second. Okay, that's the definition of frequency. So here's this red object going up and down at a very low frequency here, up and down like that. Period is the time it takes for it to go through a complete cycle. So let's say we start at the top, like right now. How much time does it take to go to the bottom and then return to your starting point, the red source? That's the definition of period. Okay, so now let's go back to our notes here. Okay, so here's the deal. Before we can start sound, it's important that we know how to measure wave action. Waves are created by sources that, and now pardon my writing, that vibrate. Wow, I think my pen is broken. Anyway, that vibrate, okay, or oscillate is the other term for that, in a repetitive fashion. Now, when something is moving like this, we can describe it using frequency. Oh my goodness. Wow, it's awful. Okay, frequency. I think I need to buy a new pen. And period. These pens are $100 too. What a ripoff. Anyway, so frequency and period. Okay, so now period, let's start with that. Period is defined as the amount of time, okay, it takes to complete a cycle. Now, a cycle is one complete vibration motion, okay, of the repeating motion. So like say for your bicycle tire to spin around once, okay, that's one cycle. Or for your hand to go up and down, like go start up, go down and back up again, that's one complete cycle. The moon orbits the Earth once every 27 days, in case you forgot that. So its period, days, okay? So its period is 27 days, of course. Now the period of rotation of the Earth is 24 hours. Remember we talked about that before? But the period of revolution would be 365 days. And again, my writing is terrible. Unfortunately, I can't do anything about it until I fix this dumb pen. I don't know why it picked today to break on me. I think I actually might have dropped it or something. I don't know. Okay, anyway, so here's some examples. There's a formula for this, okay? So the way you calculate period is by using this formula. Period is equal to the amount of time divided by the number of cycles. So we use capital T for period, okay? We use little t for time, and for cycles, we use N for number of cycles, okay? So here's an example where a buoy is bobbing up and down in the water because of water waves, and it bobs up and down 10 times in 60 seconds. Now the question is, what is its period? Well, it's time over cycles. So that means 60 divided by 10 equals 6 seconds per cycle. Okay, sometimes we just say 6 seconds. Okay, 6 seconds per cycle. So you get it? It bobs. It takes 1 second for it to bob up and down once. Okay, that's what period means. How much time it takes for 1 cycle. Now, here, and by the way, you can print this page and follow along and fill it in yourself. I highly recommend that. Okay, these are notes for you. So anyway, now frequency is defined as the number of cycles per unit of time. Now notice how closely it's related. I'm not even going to try to write it nicer than that, guys. Like, you just have to understand my pen is really bad. Anyway, what you have to understand, okay, is frequency is defined as the number of cycles per unit of time of the repeating motion. And okay, for example, you see how closely it's related to period though. Period is the amount of seconds per cycle. Frequency is the exact opposite. It's what we call the reciprocal of that. It's the number of cycles per unit of time, okay? So, for example, let's say a piano string vibrates 440 times in 1 second, and that is A2 on the keyboard, so it's an A. Okay, its frequency would be 440 cycles per second. Now we have a special unit for cycles per second, named after a scientist called Heinrich Hertz. H-E-R-T-Z, and here for short, capital H, and it has to be a capital H, small z, okay? That represents the symbol for frequency. Now what it means is cycles per second, okay? So how do you calculate frequency? Well, it's the reciprocal of period. So instead of going time over cycles, we do cycles over time, okay? So it's n over t. That's the frequency. Now, here's an example. A tuning fork vibrates 1,500 times in 3 seconds. What is its frequency? What would be 1,500 divided by 3, which is 500 cycles per second, or 500 hertz. Okay, so it's 500 hertz, and that would be the frequency of the tuning fork. All right, now, if you examine these two equations, period and frequency, so this is an important key point, they're reciprocals of each other. So therefore, T is the reciprocal of F. So T is 1 over F. Or you could write, I hate writing on this thing, I could write F equals 1 over T. Okay, and I really have to write that in a very deliberate way for it to look legible. It's the same thing, and so 1 over something means it's the reciprocal function, and that means you just take the fraction and turn it over. Okay. All right, so when you come to school on Tuesday, we're going to do this lab activity, which is the frequency of a pendulum. Okay, period and frequency of a pendulum. So we'll do that in class. I'm not going to do it here for you. Pendulum is just that thing that swings back and forth, like we can hypnotize you with it. So I'll try to hypnotize you, on Tuesday. Okay, so that's exciting. Maybe I'll hypnotize you so that like you're a good student, right? Because let's say like you're pretty good, but you could be even better. Well, maybe we can fix that with some hypnosis, right, in a pendulum. Okay, so anyway, we'll leave that for Tuesday. All right, moving on. Okay, so I promised that I would label a diagram here. So we have different kinds of waves. So please remember what a transverse wave is. What a transverse wave is it has crests. So those are peaks. I'm going to try to write it. Peaks. Okay? And troughs are, wow, it's bad, valleys. So you have peaks and valleys, crests and troughs, and here this thing called a wavelength is the distance between two valleys, or it could also be, and this is going to be bad because my pen is bad, it could also be the distance between two crests. Now we actually have a special character or variable that we use to represent wavelength. I'm going to get you used to it right now. The special character is a Greek letter, and this is going to be so bad me writing this today. Actually, it's not bad. Okay, so that is lambda, it's called, is a Greek letter, and it's equal to, in physics, it always equals equal sign, except for one class, the wavelength. And again, I am really sorry that the pen will not lift off the screen for you, but that's it. Now, here's the deal. A longitudinal wave doesn't have peaks and valleys. It has compressed areas. So I'm going to use the highlighter here. It has compressed areas that are called compressions, okay, where the spring loops are squeezed together. And the opposite of a compression is this weird word called a rarefaction. Okay? Rarefaction is when things spread out. Rarefied air means like the air molecules are further apart. There's more space between them. So that word, that odd word that you probably never heard before is called a rarefaction. Now I'm going to label another compression here, and there's another one over here. Okay, that's just starting. The distance between two compressions, the distance from here to here, is still a wavelength. And I'm going to use my Greek letter lambda from now on to represent wavelength. Okay? Now, amplitude is how tall a wave is. And this line is called the equilibrium line. Equilibrium. That's like the still. Oh my goodness, it's awful. The still water line. Okay, the still water line. Wow, this is intolerable. I have to go straight to the store and buy a new pen tomorrow. Okay, so this is really terrible. But anyway. Okay, so imagine like you're out in the ocean and there's no waves at all. So that's the still water line. In other words, that's undisturbed water. Well, the peak rises above that line, okay? And the trough goes below it. So the still water line is how we measure how tall the wave is. So the amplitude, I'll just put the letter A here for amplitude, is how tall the wave is. Now, it's also how deep the valleys are. That is also amplitude, okay? So that is a way of measuring the height or the depth of a wave. Is something called amplitude, and we always measure it from the still water line. Now, it's really hard for me to show you how you visualize amplitude on a longitudinal wave because it's not how tall it is, but rather, you know, if you take a dot, we know that the dot goes forward and goes back. It gets pushed forward by the crest. So this is its, if you like, it's in the center here. I'll use red. Let me see if a different color works better. So here's red. So here in the center is its equilibrium point. No, it doesn't work any better. So that's its equilibrium point. So here you would measure amplitude from that point, how far it gets pushed forward and how far it gets pushed back. That would be its amplitude also. So it's not going up and down like it does with peaks and valleys. The particles are going back and forth, remember, in a longitudinal wave? And so amplitude is how far they go forward from their resting spot and how far they go back, okay, when they get pulled back. Okay, so that's it. Okay, now that's the sort of the basic characteristics of waves. So you know what a wavelength is, you know what an amplitude is. We've learned frequency and period. Okay, so you have when you have wave after wave after wave, we can talk about it in terms of frequency and period. Now let's finish today's lesson with something called the universal wave equation. Okay, and then there's some homework in the textbook on this. I'm glad I already have handwriting here, so I don't have to write it again. All right, so here I have that familiar picture, and from now on, when I draw waves, I'm not going to draw longitudinal waves because those are really hard to draw. Even if I had a good pen, they're really hard to draw a longitudinal wave. So instead, what I'll do is I'm going to draw a transverse wave, okay? Just to represent waves because they're easy to visualize. Now, here's the deal. I'm just going to use my highlighter. So here these waves are traveling, these crests and troughs are traveling to the right, okay? So they're moving to the right, and the particles are moving up and down as this wave goes by. So here's the deal. We know that speed, a formula for speed is just the distance something travels divided by the time, right? So how long does it take the wave to travel so many meters? We can measure the speed of the waves. Okay, you follow me? Okay, now speed is distance over time. So if you were to run a 100-meter dash in 10 seconds, we could say, okay, your average speed would be your distance, 100 meters, divided by 10. And that would be equal to 10 meters per second, right? So we can do the same thing for waves. But here's the deal. If the distance happens to equal a wavelength, so let's say we're standing in the water and we measure off, okay, this is the length of a wave, then the time it takes for the wave to travel one wavelength is by definition the period. Okay, so T here is the period, okay, of the waves. So therefore, the speed of the wave would equal distance over time, or in this case, wavelength divided by period. okay? And since period is the reciprocal of frequency, I can replace the 1 over t with just f. So here, what I'm going to highlight for you in the box, and let's say what I just showed you is where the equation comes from. Let's say you don't understand where it comes from, you're having a hard time following. Okay? All right. I'll be able to make it a little more clear in class for you on Tuesday, but you don't need to know where the equation comes from to answer the questions. Okay? So you just have to use the formula. So this is a formula, and if you like, I can make a triangle for you. I'll do the best I can. It's an annoying pen. Okay, you'd put V up here, F there, and lambda there, okay? Or V here, lambda there, and period there, okay? And you know how to use the triangles if you're trying to isolate a variable, so that's what the homework today is about, okay? It's about doing things like that. All right, so let me give you an example, okay? Now, V represents speed, I guess it's velocity, okay? That's why we use the letter V. F represents frequency, it's in hertz. Lambda is wavelength in meters, and we call it the universal wave equation because all things that are waves, whether they're longitudinal or transverse or torsional or otherwise, must obey this formula because it's true by definition, okay? And so it's universal, meaning for all waves. Like if I had the universal blood type for donor, which I actually do, okay? That means like anyone can take my blood, right? Like anyone could have it. And so that's called universal donor. So universal means not anywhere in the universe in this case, it means all people could take it, right? So in this case, universal wave equation means all waves must follow this basic formula. They must be defined by this formula. So we call it the universal wave equation. Works for all types of waves, whether it's light, sound, water waves, or even waves in a skipping rope or guitar string or musical instrument. Regardless of the wave, they must obey that simple principle. Okay, now let's do the example of radio waves. So here I already have an example for you. And last time I taught this, I asked the students, all right, name me a radio station. So they said, okay, Hot 89.9. Now Hot 89.9, I don't listen to that radio station, but I do know, I listen to CBC of course because it's educational. So I'm doing that for you. Anyway, the number 89.9 is measured in megahertz. Now, that's a metric thing, so I'm going to remind you that capital M equals mega. Remember when we did the metric system? And mega means 10 to the power of 6 hertz. So 10, it means, forget it, I won't write hertz, it's just 10 to the power of 6. So here I'm doing my calculation. The frequency, okay, fortunately the highlighter is not affected too much by this pen problem. It still does it, but anyway, the frequency is 89.9 megahertz, which is 89.9 times 10 to the 6 hertz. So I replace the mega with 10 to the 6, okay, to convert it to hertz. Now all light travels at a known speed of 3 times 10 to the 8 through the air, meters per second. So it's 300 million meters per second. Light is very fast, okay? So now my question for you is, what is the wavelength of these waves coming from that radio tower? How long are those waves? So let's use the universal wave equation to find out. So lambda will equal V over F, just solving the equation for lambda. And then I plug in the numbers, 3 times 10 to the 8 for the speed, divided by 89.9 times 10 to the 6 is Hot 89.9's frequency, right? And I end up getting 3.34 meters. So how far apart are those radio waves coming from that radio station? They're actually about 3 meters apart. They're pretty long, actually. Okay. Anyway, that is radio waves. Pardon me, now I'm getting tired. Okay. Now, how about something even more devilish, okay? Wi-Fi, the bane of our existence, our children destroying you with cell phones, okay, and screens. Anyway, Wi-Fi, we turn it off at home when the boys need to have a break, okay? We don't give them a choice. So is it like that at your home? Okay. I kind of hope it is because, you know, I think it's a good thing. All right, so here's the deal. The frequency of Wi-Fi, the low band of Wi-Fi at least, is 2.4 gigahertz. Now, giga means 10 to the 9. Okay, it actually means it's 1,000 mega, which means 10 to the 9 instead of 10 to the 6. Okay, so again, we'll repeat our calculation. It's still light. Wi-Fi is still a radio wave, and so it still travels at the same speed, 3 times 10 to the 8. But how long are these waves? Well, we put the numbers in, and we get 0.125 meters. That's just 12.5 centimeters. So these are a lot shorter, okay? And the thing about Wi-Fi signals, what do you know about Wi-Fi? Okay, so Wi-Fi signals are great for your house, but they don't have a lot of range, right? So in other words, if you walk down the street, you're probably not going to pick up your own house's Wi-Fi after you've gotten maybe 100 meters away or so. That's because the short wavelengths don't travel as far, and they're not very good at getting through walls. Not terrible, but not great. And that's why if you have a house with a lot of walls and everything, your signal, your Wi-Fi signal, will tend to not be great if the router is behind. There's a lot of walls between the router and you, okay? However, okay, radio waves, look at those. Now we have this antenna that's like kilometers away from you. Who knows? It could be 50 kilometers away from you right now, that hot 89.9. And yet you can hear, you can tune in that radio station on your radio right through the walls of your house. Okay, and it could go through 5 or 6 walls and we can still hear it clear as a bell. Why? It's because long waves travel better through solid objects than short waves. And so the longer the wave, the better signal penetration. Now the problem is long waves don't carry a lot of data. So we can't put our Wi-Fi to low frequencies, which means really long wavelengths. We can't do it, okay, and get a lot of bandwidth, which means a lot of, like, you know, when you have like your phone has a slow internet connection. Well, if you were to use really low frequency radio waves, they'd be great at getting through the wall, but your data speeds would be really low, okay? And so what we prefer is using Wi-Fi, which has 12 centimeter waves, okay? 12 centimeter waves, that'll get through the couple of walls, you know, maybe not more than 2, okay, 2 is pushing it, but 3, forget it, 4, forget it, 1's okay. So it has some ability to get through the wall, but not a lot of range. And so, you know, if you have a really big house, you'll need to get a Wi-Fi extender or a mesh, like a network mesh router, okay, to spread out your signal between all the rooms. Okay, anyway, that's it. So there ends the lesson, guys, for today. Universal wave is really easy. Math is super easy. Okay, we've learned one equation, that's it. Or, well, I guess there's 2. There's one for frequency and period, and there's another one for the universal wave equation. But that's it for today, okay? Now you can ignore these other lessons here. We'll talk more about those when you get to class on Tuesday. But as far as the homework goes, can you please do, okay, tomorrow, before you come in on Tuesday, I want to see this finished, okay? And it is lessons 1 and 2. Universal wave equation, okay, and frequency and period. Now the homework, it looks like there's a lot of questions there, but they're all like quick. Just plug the numbers into a formula. So please do it, and please bring, I know you'll have questions. If you do your homework, you'll be able to ask in class. That's what I want. So please get it done, and there you go. There's your first lessons in this unit. Okay, so thanks for putting up for the glitches and technical errors here. I'm going to stop the lesson here for today. It's less than an hour. It's 49 minutes. But that included a course outline. The actual lesson is probably 10 minutes shorter than that. So that's not too bad, okay? Use the other hour and a half. You owe me 2.5 hours every day, okay? Every day, 2.5 hours, whether you're at home or at school. So tomorrow you're at home, cohort B, please do this homework. I would say altogether that homework wouldn't take you more than half an hour. So I only took 50 minutes of your time today. So that gives you another hour and a half to do homework. I'm only saying it's taking half an hour. That gives you a free hour. So you're welcome, guys. All right. I'm sorry for all the technical difficulties, though. Next time, I'm sure I'll have it fixed. Okay. I will have less money in my pocket, but I'll have a new pen. Okay. So take it easy, and we will see you. I guess if you're watching this on Monday, I'm recording this on Sunday night. But if if you're watching it on Monday, which you probably are, then I will see you tomorrow. So exciting. Okay. Don't forget to bring in your textbooks from last semester, or like not the one you had with me, but the one you had with your other teacher, because they're due. You have to bring those back in. And so please do that. And we've been told to tell the students to just, go and see your teacher from your last quad and turn in your textbooks. So don't forget that. All right, guys, we'll see you tomorrow.